Galaxies lacking dark matter. What are they? Where are they? How many of them are there? How do you even make them? For the dark matter aficionados in the room, hopefully I can convince you that the galaxies themselves are lovely. And the reason I love them is because galaxies are a lot like you and I. If you pay attention to my accent or my mannerisms or the music I like to listen to, you can learn something about my family, my history, my culture. The same is true with galaxies. If you pay attention to their morphology, their kinematics, their chemical composition, you can learn something about their assembly history and their interaction history. And speaking of history, I'd like to acknowledge that we're on Chumash land, indigenous land. I'm a person of indigenous ancestry. I'm Kikapu from my father's side and Huichol from my mother's side. So it's really important to acknowledge this. Also to acknowledge the people who are in here, the people who clean our rooms, the people who take care of the landscapes, the people who cook our food. Many of them are as curious about the universe as you and I, but they didn't have the opportunities we do. Now, when I talk about indigenous people and indigenous land, I want to join Chanda in urging you to also talk about Palestine. It's many of the things that are happening in Palestine mimic what happened to my people in the United States. The killing of people, the taking of land, the erasure of culture, and the erasure of history. Fortunately, there are many historians, including many amazing Israeli historians, who are keeping track of this history. But it's really important to call out hatred anywhere we see it. So the story begins in a group called NGC 1052. This is 20 megaparsec away. This is an intermediate mass group. And I'm zooming into a satellite of this group. There's this little fuzzy blob here. This is called NGC 1052 DF2. And it's called DF2 because the people who found it used the Dragonfly telescope to find it. It's a really cute low mass galaxy, around 10 to the 8 solar masses. So this is another look of this galaxy. And this was discovered in 2018 by Peter Van Dokkum and collaborators. And they wrote this really nice Nature paper. And I want to make a disclaimer that I'm not a co-author of this paper. I have literally been invited to other continents to give colloquia so they can attack me about this paper. And I'm like, they are disappointed because I'm not a co-author. But what they did is when you look at the stellar light, you can estimate the stellar mass. But this galaxy has a lot of globular clusters. So if you follow the dynamics of the clusters, you can also infer the dynamical mass, the total mass. And for this specific galaxy, when you compare the two, you see that they find that they are consistent with each other, meaning that there isn't room for dark matter. This is a dark matter conference, so this is really nice to talk about this. The following year, in 2019, they found another system like this in the same group, and I'm going to call them DF2 and DF4. And there were a lot of controversies about these galaxies. On the observational camp, people were like, well, maybe you got the distances wrong, or maybe the membership of the clusters is wrong. And on the theory side, some people were like, well, this proves that lambda CDM is wrong. You should just get rid of CDM altogether. Or people say, like, hold up, maybe we need to make dark matter self-interacting. If you look at cosmological simulations with dark matter and baryons, none of them were able to reproduce galaxies like this until we came along. So now let me tell you a little bit about a few of the theory ideas that emerged regarding these galaxies. And the first one actually happened 20 years before these galaxies were discovered by Priya Natarajan and others. Joe Silk is the last author. If you know Joe, this is a very Joe Silk kind of paper, you know, like really, you just have a wild idea and you just write a paper. So this was the idea that if you have a quasar, you have outflows that can actually trigger galaxy formation. You can compress gas and that makes galaxies without dark matter. So that was the idea 20 years ago. I'm a member of the FIRE collaboration. So with FIRE, we've been running simulations with AGN feedback. And I'll mention two papers by Jonathan Mercedes Feliz. He's an awesome grad student at UConn. And the first paper focuses on putting AGN feedback in our FIRE simulations. Putting AGN feedback in simulations that resolve the turbulent multi-phase structure of the ISM is really difficult because you have to increase resolution when you get closer to the black hole, and that doesn't only mean resolution in mass and space, but also temporally, because this process has really short dynamical times. So running this in a full box is basically impossible. But with this kind of zoom simulations, you can do it. And what happens is when you have so you have this Dawson-shrouded nuclear region of the galaxy, and you have the quasar, and that blows out that region, and then the object is clear. But it turns out that when you have that blowout phase, you can actually compress surrounding gas and make stars. Generally, it's been known for 20 years that AGN feedback quenches galaxies. It stops star formation. But if you look locally, you can actually trigger star formation. We call this positive feedback. And we also make a prediction. If you're looking for new stars or star-forming gas that is triggered by AGN feedback, you need to look at outflows. So it's usually in the outflows, you see outflow in star-forming gas. That was probably triggered by the AGN feedback. It would be nice if we had made an actual galaxy like Joe Silk proposed. We don't quite do that because it happens inside the galaxy itself. But something really curious happens in some extreme cases. So the green particles are gas. When you have the AGN going off, something that happens is you compress the gas and you're able to make star clusters. So when these particles become yellow, that means that they're becoming stars. And we're able to make the star clusters due to AGN feedback. I am someone who loves to think about the boundary between what is a galaxy and what is not, especially globular clusters. And it turns out with AGN feedback, you can make these massive star clusters that can live a long time inside the galaxy itself. I was hoping you would be able to make them outside the galaxy and have these dark matter efficient galaxies a la Joe Silk. Unfortunately, you couldn't do that. You would need more energy, more power in the quasar, and that would actually destroy the host galaxy itself. So that mechanism, although it's really interesting, it doesn't really work out. The second proposal was from Peter van Dokkum himself, and this is a collision of two low-mass galaxies. So you might know about the bullet cluster. You have two massive clusters. When they collide, the dark matter just passes through because it's non-collisional, and the barriers stay in the middle. So he said, well, maybe this is happening at smaller scales. You have two low-mass galaxies. One of them is coming at really high velocity, and when they crash, the debris in between creates a new galaxy. So that's a scenario they propose. And I have many issues with this scenario. So the first one is, well, they say you need to have a satellite sitting there, and then another galaxy comes at really high velocity. And it has to come with a velocity that is much higher than the virial velocity of the host halo. But on top of that, this has to happen a long time ago, a high redshift, when that halo was even smaller. So it's really difficult in cosmological simulations to reproduce such high velocity collisions. It could happen, but it's really unlikely, and we don't find it in our simulations. Another issue I have with this picture is people have been doing idealized simulations where they say, hey, we actually make these things, but those simulations use a really old version of a gadget that has really a lot of problems with mixing gas. So in those older simulations, you have numerical artifacts that prevent you from dissolving gas. So I think that's one issue I have with these simulations. Another one is those simulations don't have feedback. So I imagine if you put supernova explosions, that gas would be immediately blown out and you wouldn't even make a galaxy. At most, if this were to happen, at most you would get maybe a trail of stars, but definitely not a trail of galaxies. But that didn't deter my friend Peter van Dokkum from claiming that maybe, you see in this group, we have a line of galaxies, a perfectly alignment of galaxies, so this has to be the mechanism. Now, the problem I have with this picture is that the error bars in the line of sight direction is about half a gigaparsec, not half a megaparsec, so about the virial radius of the host halo. So most likely this is maybe a plane of galaxies. Just because you see a line of planets in the sky doesn't mean that they are in a three-dimensional line. So unless they show me this with really small error bars in the line of sight distance, I'm not convinced that this is a line of galaxies. So yeah, Peter, like Joe, have really good ideas, but I disagree with them. The next scenario is I think this is the one that resembles ours the most. So when these papers came out, Go, Gija, and Frank, who's here, they ran idealized non-cosmological simulations where you have interactions between a low-mass galaxy and a massive galaxy. And I think our scenario resembles this the most. So I'm not going to call mine 4, but 3 prime. For many reasons. One, because Frank is in front of me and I'm chicken shit, I'm afraid of him. But also, there are some differences. This is in a cosmological simulation, and I love numerical experiments. I've built a career doing them, but this is in a cosmological context, and this is with full fire feedback, astrophysics, and everything in it, right? And another thing that's different from Frank's scenario is that in these simulations, when the collision happens, these are gas-rich objects. So in addition to the gravitational tidal forces, you also have collision between gas and gas particles, which makes things really messy. So this is done with Firebox. Firebox is a cosmological simulation with fire. Fire stands for feedback in realistic environments. You probably heard of simulations like Eagles and Illustros TNG. The difference between fire and those simulations is that here we resolve the multi-phase turbulent structure of the ISM, and 2, star formation is regulated by feedback. So this is what we find. Because DF2 and DF4 are low mass galaxies, I'm going to focus on the low mass regime. I'm not going to go above the LMC. So on the x-axis, I have stellar mass. On the y-axis, I have dark matter mass. I can add some lines to guide the eye. This is color-coded by the fraction of dark matter. If you're extremely pink, that means you're dark matter dominated. I can split this plane into the dark matter dominated and dark matter deficient regime, and I can include the observations, DF2 and DF4. Now, Van Dokkum, they only measure quantities within R12, within the radius containing 50% of the stellar light. So everything I'm showing you here is within the radius containing 50% of the stellar mass. And here I'm only showing you central galaxies, the dominant galaxies in each dark matter halo. When you include satellites, this is what happens. So the triangles, they begin on the relation, but because of tidal forces and ramp pressure stripping, they lose dark matter, so they go down, and they lose stars, so they move to the left, right? But some of them, 7 of them actually made it below the line. We find in Firebox 7 dark matter deficient galaxies. I call them wolf, wild potato, pain, long hair, bluebird, and deer. And you might be wondering, what's up with those names, right? So I'm a person of indigenous ancestry, but I'm not Cherokee. I have a good friend who's Cherokee, who has told me about the 7 Cherokee clans in the tribe. So he put me in contact with elders in the tribe, and I asked them permission to use the name in honor of their clans. And each of the clans has a different personality, a different culture, a different cuisine. There are matriarchies, so the lineage goes through the mother as it should be. And my galaxies also have their own personality and their own history. And I'm not going to talk about all of them, but I'll show you 3 of them. So this is deer, blue, and bird. They live in the same group. And this is a mock Hubble Space Telescope image of the simulated galaxies. And if you look at the dark matter distribution, you see that there are no subhalos associated to them. So many of you have probably heard of the missing satellites problem. This is the opposite of that. This is the missing subhalo problems. Because, you know, to get promoted and to get tenure in this field, you need to provoke people and piss people off. So I made myself a problem and got tenure. Anyway, so how do you make these things? So I'm showing you the main plot in my paper, and what I'm showing you here, this is the stellar mass ratio of the satellites in the simulation relative to their central galaxies. And I'm only looking at satellites between 10 to the 8 and 10 to the 9 solar masses. And on the y-axis, I have the minimum distance between the satellite and the central between infall, so you're orbiting, until today. And this is scaled in units of the virial radius of the host dark matter halo. And this is the stellar mass ratios for DF2 and DF4. We don't know their dynamical history at all, but we know the stellar mass ratios. So we know they are somewhere there. And this is where the 7 dark matter deficient galaxies are. The numbers next to the name indicate the number of pericentric passages. Some of them are really persistent, like blue has been around 9 times and bird 14 times. So they occupy a really unique region of parameter space. Now, as Asi was telling us before, when you're a satellite galaxy, you have 2 choices. Either you assimilate, you merge with the massive galaxy, you assimilate to it, or you're completely disrupted. So the reason this region is empty is because dynamical friction is sufficient when the 2 galaxies are somewhat similar. The moment you show up in that region, you merge. On this side, if you have extremely high stellar mass ratios, the galaxy just dissolves. So, but these galaxies, they chose a 3rd path. They're like, we're not going to assimilate, we're not going to dissolve, we're going to persist, and we're going to be here. So these galaxies remind me of my own history. So I'm a person of indigenous ancestry, but I have a European name. I was assigned a European gender. I only speak European languages. I tend to wear European clothes, but I'm an indigenous person. And we lost our culture, we lost our language, just like these galaxies lost their dark matter, but I am still here. Thank you for your generous attention. What questions do you have for me?